Friends, welcome back to another edition of Miss Faust's Algebra 2 notes. We're getting close to the end of this unit already, believe it or not. And the next thing that we're going to look at today actually builds exactly on the last thing. Go figure, math is related. Whoa! I know. Okay, enough of me babbling. Today we are looking at lesson 7.4.2. I called this A because there are going to be two videos for this. This is the first one. Our essential question is how can we find all the roots or zeros of the polynomial p of x equals 0? So we've been working hard on factoring. That's going to be the key to this too, is factoring. So all those tools we've been using, they're just going to keep coming back. To start off our notes today, we have a very important fundamental theorem of algebra. So I know you're like, oh my gosh, I've been doing all these years of algebra and I'm just getting to the fundamentals, and you are. But that's okay. So this is part one of the fundamental theorem of algebra. And what the fundamental theorem of algebra states is that every polynomial of degree n greater than or equal to 1 has exactly n zeros or roots. So what that means is if we draw a graph of any polynomial, we're going to be able to look at it and we're going to see where the zeros are, right? And if we have, sometimes we have repeated zeros, so we might have like x plus 2 squared in our problem. That would be where we'd have a little parabola at the -2. And some might be imaginary. So some of them won't show up in graphs like we're used to seeing, but we'll know that they're there because whatever the degree is, that's how many roots you have to have. So if you graph a 4th degree polynomial and you only see 2 points where it touches the x-axis, you know there's 2 more that are missing, and those 2 are going to be imaginary. And today, I'll show you how we find those. So to go back, this builds again on what we were doing last time. So what we're going to use the fundamental theorem for is to find all the roots or zeros of a polynomial. And you've actually done this with quadratic functions before. This is just showing us how we take that to the next level for cubic and quartic and more complicated functions. So what we want to always start by doing is factor as much as possible. So if that's that yellow sheet I gave you in class, if you have a greatest common factor, you take out the greatest common factor. If you can use difference of squares, you use difference of squares. You do whatever you can, and you get the problem factors as far as you can. And really here, your goal should be to get no exponents higher than 2. Okay? Because if you get down to no exponents higher than 2, then you can use a quadratic formula to solve it the rest of the way. If you still have exponents higher than 2, you want to use those factoring methods, which could include synthetic division, till you're down to less exponents. And then, once we've factored it, remember we're going to have a whole bunch of factors then, parentheses. So then we set each factor equal to 0, and we solve. So most of those are going to look like things like x plus 1 equals 0, or 4x plus 1 equals 0, or they might be quadratics, x squared plus 5x plus 6 equals 0. But either way, we have strategies to solve those. So that's always going to be, that's why we've spent so much time on factoring, is because that's really what we have to do again and again and again in these, and we have to keep factoring it down into smaller and smaller and smaller pieces. So let's look at an example. I'm just turning the page so I'll have plenty of room. You probably have room still on the page you are on. So your questions will go here. My notes will go here. Both of my dark pens are dying, but I will get new pens soon. So, first example I have, here we go. So, factor p of x equals x to the 4th plus 5x to the 3rd plus 6x squared minus 4x minus 8 completely, and find all roots. So really remember, when we're factoring, we're really close to having the roots. It's really just sort of one little extra step. So what we want to think about first, so our polynomial is x to the fourth plus 5x to the third plus 6x squared minus 4x minus 8. So first I'm going to find my possible zeros. Remember, to find my possible zeros, I need to do m over n, where m are all my factors of 8. So m is plus or minus 1, 2, 4, and 8. N is just plus or minus 1. N's all my factors of the first term. So all the factors of that divided all by all the factors of that just give me those. So that's plus or minus 1, 2, 4, and 8. Once I've found the possible zeros, then I'm going to try some. Okay, so this is where we go through and we try the different ones to try and see which ones work. Now you can start with hard ones if you want, like 8 and negative 8, or you can start with easy ones like 1 and negative 1. I like to start with the easy ones, but really it's up to you. I'm going to start with negative 1 first, just for fun. So if I start with negative 1, I put that here. Then I need a 1, a 5, a 6, a negative 4, and a negative 8. So I'm just going to check this and see if negative 1 works. Bring down the 1, negative 1, 4. 4 times negative 1 is negative 4. 6 plus negative 4 is 2. Negative 1 times 2 is negative 2. Negative 4 plus negative 2 is negative 6. Negative 1 times negative 6 is 6. That's negative 2. So that did not work. That tells us two things. That tells us x plus 1 is not a factor. And it tells us x equals negative 1 is not a root. Okay, so the difference between the factors and the roots is just which ones actually make it equal, or setting it equal to 0 and solving it. So x equals negative 1 is not a root because we didn't get 0, which means that. Next I'll try 1. So here I tried negative 1. Here I'll try positive 1. Because, you know, why complicate things if we don't have to yet? 6, negative 4, negative 8. I'm just reading off those while I'm babbling. Babble, babble. 1. 1 times 1 is 1. 5 plus 1 is 6. 1 plus 6 is 6. 6 plus 6 is 12. 1 times 12 is 12. Negative 4 and 12 is positive 8. Whew. 1 times 8 is 8, negative 8 and 8 is 0. So, what that tells us, this did work. So that tells us x minus 1 is a factor, and it tells us x equals 1 is a root. So what I want to do is I want to take this factor and I want to rewrite it now. So 3, I'm going to write my new factored form, because that simplifies my problem. And I left space over here because remember, these numbers are what go in my factored form. So my first factor is x minus 1. And my next factor is all of these. So 1, instead of x to the fourth, I go down by 1. So x to the third plus 6x to the second plus 12x plus 8. So we look at this and just remember, this gets the x to the third, that gets the x squared, that gets the x, and then the 8, so that's where those come down here. Okay, but now in this problem, oh geez, which you can't see all of right now, but I can fix that. Notice here, I still have an x to the third. So what I have to do is I have to keep going with my synthetic division. And I keep using synthetic division until I get this exponent less than 2. But I can now do synthetic division on this simpler problem. So it's not quite as much work. It's one less problem than I had before. And I can still use the same list of numbers, right? So I already used 1 and negative 1. Next I'm going to try negative 2. So here I'm actually repeating number 2 with that part of my problem. So I'm going to put negative 2 on the outside of my box, and now I'm going to use 1, 6, 12, and 8. So I get 1, negative 2 times 1 is negative 2, 6 and negative 2 is 4, negative 2 times 4 is negative 8, 12 plus negative 8 is 4, negative 2 times 4 is negative 8, that gives me 0. So that tells me x plus 2 is another factor. So I've now found two factors for this. Remember, I'm looking for 4 because my original exponent was 4. So what I can do now, remember my first factor was x minus 1. So p of x, as I'm working on getting it factored, I know it has an x minus 1 first. I know it has an x plus 2 because I just found that one. And then I know it has a 1x squared, a 4x, and a 4. So I put x squared plus 4x plus 4 here. And now I'm so close. Now I have a quadratic out here. So if I wanted to now, I could actually stop altogether, but this still factors. So I want to keep going a little bit further. Let me go on to the next page. You know, I write big, so I run out of room. So let me just recopy what I had before. So p of x, I've now got to x minus 1, x plus 2, and x squared plus 4x plus 4. So now what we want to do is we want to factor this part. That's a trinomial, remember? So we think about the box, or we notice there's nothing in front of the x squared. So we think of the two things that multiply to 4 and add to 4, which are 2 and 2. So we get x plus 2 and x plus 2. So this is completely factored. That last x plus 4, or whoops, x squared, 4x, and 4 became the x plus 2 and x plus 2. So what we've got here is we've got repeated roots. So p of x really equals x minus 1 times x plus 2 cubed. That's our completely factored form. For the zeros, we just take each one of those and make them equal to 0. So if x minus 1 equals 0, x is 1. We actually also found that before because 1 was what worked here. So we kind of already knew that, but sometimes we forget by the time we're done. Here, cube root of 0 is still 0, so that just means x plus 2 is 0, or x is negative 2. So x is negative 2. Again, we had that one down on the last page. We had it down here. But we only knew that it had a multiplicity of 1 then. So what we say, because this one shows up 3 times, is that it has a multiplicity of 3. So the zeros for this are x equals 1 and x equals 2 with a multiplicity of 3. So then if you take 3 of those plus 1 of those, you get 4. There's 4 zeros. All of them in this case were real. So again, just to make sure everybody's clear, the question asked us to factor completely and find all zeros. So our completely factored form is right here. And our zeros are here, here, and here. So zeros are 1 and negative 2 with a multiplicity of 3. I don't know what that thing is. We'll make it an arrow. Okay, so completely factored and zeros. Okay, I want to show you one more example, and this one magically appeared, I know, in front of you, but you can stop and take a minute and write it down. So we have p of x equals x to the 4th minus 6x squared minus 27, and again we're trying to factor completely and find all the zeros. Instead of going through these synthetic division steps like I did in the last problem, I think people are pretty good at that. So I'm going to just take us to where this would be new. So where this would be new is we would have started factoring this, and what we would have found is we would have found that both positive 3 and negative 3 give us 0 when we do our synthetic division. So we would know that x plus 3 and x minus 3 are two our 2 roots of this. And then we'd still be left with an x squared plus 3. So I'm not showing you that work, but in between, magically, this, we're using synthetic division to find the first 2 factors. Okay, and I'm just not going to do that in the interest of time and interest. Let's admit it. You're not really that interested. So once we get to here, we look at this x squared plus 3, this can't be factored anymore. There's only 2 terms there. There's no greatest common factor. 3 is not a perfect square, and this is a plus, not a minus. So this is our completely factored form for this, and what I want to show you is the difference in how we find the zeros now. So what we know from this is we know that x plus 3 could be 0, we know x minus 3 could be 0, and we know x squared plus 3 could be 0. So again, I'm just taking each factor and setting it equal to 0. And some of you won't even have to do this for the first 2 because you'll just look at it and you'll go, oh yeah, x is negative 3 and x is 3. Those are 2 of the zeros. This one we have to do a little bit of work. Sometimes we'd use the quadratic formula because we'd have x squared plus something x plus something. This one we don't need the quadratic formula because we just have 2 pieces there. What we can do is we can just solve it using square roots. So we can subtract 3 on both sides. And believe it or not, people have a harder time solving with square roots than they do the quadratic formula because they're used to looking at the quadratic formula problems, and these they kind of forget what to do. So that's why I'm showing you this one. So we get to this x squared equals negative 3. To solve that then, remember to get rid of a square root, we take, to get rid of a square, we take the square root of both sides. The square root and the square cancel, and we get x equals, remember it could be positive or negative, the square root of negative 3. But now, we think about that again, square root of a negative number, remember that's not real, so really that's like plus or minus the square root of negative 1 times the square root of 3. Going back to imaginary numbers, so x here could be plus or minus I times the square root of 3. And that really gives you 2 possibilities, plus I root 3 or minus I root 3. So when we're listing all the zeros for this, remember our exponent was 4, so we need to find 4 zeros, right? 4 is our magic number. So all our zeros are negative 3, 3, positive I root 3, and negative I root 3. So sometimes our zeros will be imaginary, and that's okay too. Those ones aren't going to show up on the graph. What you're going to see in this graph, it's going to cross at negative 3 and 3. It's not going to cross the x-axis at imaginary numbers because the x-axis is real, but those imaginary roots do still exist because we have to find 4 zeros. And that's really what the fundamental theorem of algebra is teaching us, is that we have to find as many roots as there are zeros. So we have to use those complex numbers again to come back to finding all the zeros. Okay? If you have any questions, jot them down right here in these handy dandy margins. And I look forward to seeing you all in class again soon. Thank you very much and have a wonderful day.